Second observation involving the magnet, the coil, and the ammeter is that when you change the amount of magnetic field penetrating the coil, you get the voltage that drives the current. The idea of flux is simply the integral over surface of the force dotted with the area increment, the area increment being a vector perpendicular to the area. Okay, and that would be then the integral over the surface of F dot n with respect to area, where n is the outward unit normal. Okay, well, that's the idea of flux. Hopefully your multivariable calculus makes perfect sense out of that. If not, you should review it. Voltage then is the time rate of change of magnetic flux, the flux of the magnetic field. So the magnetic field penetrates that coil. You turn the magnet, it penetrates it in a different direction, so not as much magnetic field actually goes into the coil. You could reverse the direction. So the magnetic field is coming out of the coil. That would be the negative of what you get. If you get the magnetic field going into the coil, you have changing flux from any of those situations. Alternating current is generated by rotating a coil inside a magnetic field so that you have a continual change of the magnetic flux. And other flux changes will create different voltages. The voltage is around the boundary of the surface. So the voltage occurs around the circle. So maybe we ought to note that. That voltage is around the boundary of the surface. Now, if we go over here, if we have a loop of radius r, just a single loop, and we have a voltage around that loop, in this case corresponding to a rate of change of the flux, magnetic flux through that loop, what's the electric field? Okay. That changing flux creates an electric field, and it's the electric field that results from the changing flux that gives rise to the voltage. Well, we know that voltage is electric field times distance. What's the distance around this loop? 2 pi times the radius. So the electric field is voltage divided by distance. The electric field induced by this rate of change of flux is the voltage that we get, time rate of change of flux, divided by the length of the loop. So the point is that a changing magnetic field produces an electric field. So an electric field can result from a changing magnetic field, or it can result from a distribution of charges. Talking for a second about the relevant units, the unit of flux is the Tesla meter squared. It's Tesla, the unit of magnetic field that we haven't really defined, but that's defined here. The unit of magnetic field multiplied by the number of square meters. And of course, that's going to be the unit you get if you integrate the magnetic field with respect to the area in this manner. And that's also called a Weber. German, it's actually pronounced Weber, and that's probably not a very good German pronunciation. So I'll stick with the Americanized pronunciation Weber, but be aware that you're mispronouncing it when you call it a Weber. So the magnetic flux is in Tesla meter squared, and a Tesla times a meter squared is a Weber. The unit of area, SI unit of area, is a meter squared, and SI unit of magnetic field is the Tesla. So this is just the SI unit of flux. If we divide the flux by time, then we get Tesla meter squared over seconds, and a Tesla meter squared per second is a volt. Now a volt, of course, is a joule per coulomb, and we could use this as a definition of the Tesla if we wished. But we're probably going to define it in terms of the third phenomenon. I also mentioned that K prime, no, never mind, that comes next. Okay.